So we've been looking at how this flame stabilization happens, and essentially what basically means is you have a linearly increasing velocity profile, but you also now have a flame speed that continues to decrease from the value of SL naught, and it decreases because of the heat loss to the burner as one of the effects, and the other effect is the dilution from the ambient. For like, let's say we are looking at the fuel lean flame, and therefore if you now have a air that's coming in and diluting this, it's going to decrease the SL further, and you have to keep in mind that as you now get closer to the burner, the decrease in the flame speed is going to be more because of the heat loss and less because of the dilution. As you go further away from the burner, if the flame goes further away from the burner, the decrease in the SL is going to be more due to dilution and less due to heat loss, right? And that is actually the effect along this direction. The other way to look at it is also the radial direction. As you now go closer to the as the flame stands closer to the burner, the heat loss is more and the mixing field is actually quite narrow between the premix reactants and the diluting ambient gas, whereas as you go further out you can now actually have the premix mixture going further out into the mixing zone, and the flame can actually establish itself further and further out. And what we are basically looking for is like a leading edge of the flame which is having a slope perpendicular to the flow where the SL has to match the velocity directly. And what we are basically looking for is a condition where the local SL has to match the local U. Since the U is also increasing linearly, what we should be looking for is a condition where the local SL matches the local U, and so the flame stabilization condition is locally we need to have this matching to be satisfied. Then what we look for is two occurrences. What happens when this condition cannot be satisfied? In two ways. One, if you now progressively keep on decreasing your flow velocity, right, or progressively keep on increasing the reactivity, maybe by changing the mixture stoichiometry towards the stoichiometric mixture so that the flame speed keeps increasing for the same flow velocity. So in one case what we are looking for is a relative decrease of flow velocity with respect to the flame speed, or relative increase of the flame speed with respect to the flow velocity, in which case the flame has a progressive tendency towards establishing itself closer to the burner, and ultimately you are going to get to a situation where it cannot be held at the burner rim anymore, it wants to propagate even further in, and that is actually a situation corresponding to flashback. The second situation is where we now do the opposite, which is we now try to progressively increase the velocity relative to the flame speed, or progressively decrease the flame speed by maybe going to leaner and leaner mixtures for the same flow velocity, and that is going to have a tendency for the flame to actually get established further and further out, stabilized, get further and further out, and at some point it cannot be stabilized anymore and then it starts blowing off, right. So you have two such limits of flame stabilization, two limits of flame stabilization, or one is flashback, the other one is blow off. Right. So here what's happening is progressively, we say progressively for a reason that I will explain soon, SL becomes less than UL, and here progressively U becomes greater than SL, right. So let's look at the flashback situation. So what we are saying here is, let us suppose that you had a velocity contour that is or velocity profile that is going like this with respect to x, which is r minus r, that is the x coordinate that is measured radially inward from the burner rim. And what we want to think about is a match between a limit match between u, so this is u, and SL. So the SL basically, you see what's going on, the u increases linearly and the SL for most part of the radius of the burner is nearly constant at SL naught, and then it drastically decreases within a short region and then goes to 0 ultimately when you're reaching the what's called as a flame edge, right. So we are looking for a match that would give rise to a situation when we now have a u that is at the most equal to SL. Now what happens is, if you now try to decrease your velocity, you are now going to not be able to actually satisfy this match anymore, and you're now going to have a condition where, let's suppose that this is SL, you're now going to have a condition where the u decreases, and that leads to a flashback. Right. On the other hand, if you now try to actually have a higher velocity, then this is actually the condition for flame stabilization at the rim at the most, and any decrease in velocity is now going to actually induce a flashback. But if you now try to increase the velocity further, it's now going to progressively starting to have a flame stabilization a little bit away from the flame from the burner, right. And so decrease in velocity below the value for the u slope to be tangential to SL leads to flashback. Any increase in velocity, on the other hand, leads to flame stabilization above the burner rim. That means to say, at this particular condition the flame is stabilized at the rim, and that's the most you can do to prevent flashback. Then what happens if you keep on increasing the velocity further and further, right. If you keep on increasing the velocity further and further, we have seen what is likely to happen, that is, the flame shapes itself in a way to adjust to the increasing velocity situation. Alright, we have found that with a artificially simplified condition that zeta is equal to 0 at r equals capital R, you could now say that the flame is going to be a conical shape of any angle depending upon the SL over u ratio. So for a fairly wide range of u's given a certain SL, you can actually have a flame that is held pretty much near the rim without worrying about the details of how it is attached to the rim. If you have to worry about it, then you start seeing that it starts moving a little bit further away, the edge of the flame starts moving away from the rim a little bit, and progressively. So how does it really adjust? So if you now think about the situation there, so this is your u, so, and this is like the jet boundary, and let us suppose that we now look at 3 locations where the flame is stabilized progressively. So you can say the flame is stabilized here, here, and here. Of course, when you go further and further, the flame gets curved like the way we are talking about. But what you're basically saying is, let's look at these three conditions. The way the adjustment happens is, at a lower location you now have intense heat loss. So the flame edge is actually more towards the center when compared to the other way. When you now have a less heat loss and further location, the flame can be prevalent more closer to the rim when radially when compared to if it is much closer to the rim axially. Therefore, what happens is, for the condition A, your SL actually is 0 for quite a while and then increases, and then you now have a flame stabilization condition that matches this. If you now try to increase your velocity to a, let's say, a higher value, the linearly increasing profile would increase this way, and the flame now begins to actually so the flame speed now begins to increase in such a way that you now have the match happening over here. What this basically means is, of course, looking at how this curve looks like, maybe I should have drawn it with a slightly greater slope than what or lesser slope than what I have done, but essentially what this means is, when you now increase your velocity, the flame is getting pushed up, therefore the heat loss is less. So what it basically means is, if you now think about a distance going a little bit away from the rim, right, you can see that the flame speed is beginning to rise sooner than the previous case, and the reason for that was a decreased heat loss situation. Alright, and then you could still continue to have that happen if you now think about another velocity where you now increased, but then you're really getting pushed to the corner. Beyond a point, as you now get the flame speed to increase because of less heat loss, you are progressively, so this is actually A, this is B, this is C, progressively you're going farther and farther away, and then the other mechanism of the dilution trying to decrease the flame speed is going to come in. So the rate of increase of this flame cannot actually happen so soon from the rim, and there is a cap on how much it can increase, that is the SL naught. So beyond this point you cannot really have a further increase in velocity admitted by the flame, right, and this is a mechanism of destabilization of the flame leading to a blow off condition, right. So effectively the flame speed, because of these two mechanisms of heat loss and dilution, they combine together to adjust in order to match the flow speed locally as it is being increased over a fairly wide range, but not beyond a point, right, and that's when you're going to have a blow off. So in effect, the flame stabilization condition is that you need to have a SL equals U at G equals 0 minus, that is to say just upstream of the flame, the notation used previously. And if you use now let's say Y is the distance of the flame base above the burner, then partial SL over partial Y now should be greater than partial U over partial Y, G equals 0 minus, again just upstream, right. So this is typically the condition that we are looking for when we have an equality. So when dou SL over dou Y equals dou U over dou Y, G equals 0 minus, this leads to a blow off, right. What I would like to point out is one thing here: blow off is not the same as extinction of the flame. let's see what's going on when you're having a blow off. When you're having a blow off, the SL is actually more quickly rising to its high value closer to the flame base. Okay, so the flame base is shifted over to this point, and the SL, as we now go from the flame base, burner rim, you're now having a more drastic increase in the SL. This basically shows that when you're now getting closer to a blow off condition, which is corresponding to the curve C, the SL is actually pretty high, and you're having a fairly intense burning of the flame base at blow off. Okay, so blow off is a situation of intense burning of the flame base at blow off. Extinction is the opposite of this. Extinction is where you are progressively starving the flame of reactant mixture, right. So effectively the reactivity is coming down further and further, and since you now have a heat loss situation and a dilution situation that further decreases the SL at the flame base, so the flame base is the place where you're going to actually have the biggest hit on the intensity of burning for a extinction situation, where on the whole the flame is being starved of reactants and the reactivity is coming down, the burning intensity is coming down. It's going to actually be the worst at the flame base because of the heat loss and the dilution. So burning, so I should use the right word there. So opposite effect, least intense flame base during extinction. So putting these two together, what we can see is there is a role for the velocity gradient in this flame stabilization. So one way of looking at this is, I'll look at it in both ways. One is to actually look at the velocity itself, because you have a condition here, and another way is to actually look at the velocity gradient. You can look at it in both ways. They give you slightly different pictures but not very different. Okay, so they convey the same idea. One, you have a limit like this, so this percentage fuel, and let's suppose that this is du star over dy, where du star over dy corresponds to a velocity gradient what at a flashback or blow off. And so obviously we are looking at two limits, one for flashback and another for blow off. So this is the flashback curve, right, and this is the blow off curve. And in between the two you're going to have a stable flame. Right, and see what's happening here. The flashback curve is non-monotonic, so it's increasing and then going back again. That means you should now be able to actually look at 2 points for the same gradient, and this is now a different percentage fuel at these 2 points, right. That simply means that you could restabilize the flame from a flashback situation either by going towards this region or that region. Flashback is all about having a higher flame speed when compared to the flow. So if you now are in below a certain velocity gradient for the flow, then if you are now within the stoichiometric range, you are going to have a higher flame speed. and therefore you are going to flash back. So you now enter a unstable region. So you now can restabilize by either going in the direction of fuel rich or fuel lean, because on both sides the flame speed is going to come down, right. So it's possible for us to restabilize either by going the fuel rich direction or the fuel lean direction. That's not the case with blow off. The blow off doesn't look like a non-monotonic curve. It doesn't really curve back, right. So it keeps increasing. What that basically means is, as you are going richer and richer, the flame is going to be relatively indefinitely stable against blow off. That means it's not going to blow off. It's only the lean flames that are actually susceptible to this. Why is it the case? Naturally, because of what we pointed out last time, the dilution from the oxidizing ambience. If you now have a fuel rich flame and the flame is getting further and further lifted away from the rim because of a higher and higher velocity and a higher and higher velocity gradient consequently, then you are going to have a mixing coming from the oxidizing ambience, which is going to cause a locally towards stoichiometric kind of mixture, and therefore the burning is going to be more and more intense, and therefore it's not really going to try to blow off, you see. So what this means is blow off is progressively difficult with the increasing fuel concentration. Right, and because burning intensity increases, should particularly say at the flame base. At the flame base increases. There is another way of looking at this. Of course, the question that you have to ask immediately is, what if I actually burn this in an inert environment? Is it okay if I now have, like, let's say a nitrogen ambience in which I have a reactant mixture that is coming out through the burner, right? What happens then? I'm going to allow for a nitrogen to dilute through the sides regardless of whether it's fuel rich or fuel lean. Should I expect the blow off to actually be happening for fuel rich mixtures as well? Yes, sure enough, correct. So there is a different way by which we can look at that, which is a broader stability map, so to speak. So here we just look at it in terms of velocity directly instead of velocity gradient. The picture doesn't change significantly, at least in a qualitative way. So if you now plot fuel concentration on the x axis or the horizontal axis as opposed to the vertical axis that we did earlier, then let's now say we are somewhere in the stoichiometric, somewhere here, right. That means all this is fuel rich, right. Then our flashback curve would be somewhere there, right. And maybe I should locate this a little bit further out relative to this curve. And then you have a blow off curve that keeps going like that. That is for an air ambience or an oxidizing ambience. But if you had an inert ambience, you will have a curve that goes back like this. So this is blow off in inert ambience. So it's sort of like reproducing this picture, but then I would like to point out one more thing which is beginning to look very interesting for us now, and I would imagine you should start thinking about it right away. We are now beginning to look at a space which is significantly fuel rich, right? So if you're somewhere there, what you should be looking at is you're now having like a lot of fuel that's coming in and only a little bit of oxidizer that's coming along with it, right, in an oxidizing ambience, right. What if I did not have any oxidizer at all here? It's highly fuel rich to the point of being only fuel in an oxidizing ambient. What would I get? Right. I am now progressively departing from a premix flame. So it's not a premix flame anymore, it's actually now beginning to look like closer to a diffusion flame. Alright. So what was happening all the while when you still had some oxidizer and we really had a premixed fuel rich mixture, okay, it could be flammable, right, we are not talking about getting past the flammability limit even, right. So you could have a fuel rich premix flame, alright, but what are the products going to be? The products are going to be fuel rich, right. They are still going to have some fuel that is remaining which can mix with the air downstream of the flame, not just at the base, not only at the base, not only through the gap between the base and the burner rim. What we have been talking about is this mixing effect that's happening between the flame base and the rim, so as to focus on the flame stabilization. But on the whole you are going to have a excess fuel that's coming out of the flame which would mix with the ambient and form a diffusion flame envelope that's around the premix flame. This is typical, and so long as you have this diffusion flame envelope, it's a lot harder to destabilize this flame, because diffusion flame is going to actually be there with the fuel and oxidizer or the excess fuel and oxidizer mixing all the time, and it doesn't really have to propagate against a flowing mixture, a flowing reactant mixture. Therefore the stability seems to be significantly protected for us in the case of fuel rich flames. That's what essentially is happening, right. However, there is another interesting thing that begins to happen, which is you now have to worry about something called a lifted flame. So somewhere in here you now have another envelope that is coming up in the stability diagram, where you now have a lifted flame, as opposed to which what we have been talking about so far in this region as well as here is what is called as an attached flame. That is to say, whatever we have been talking about as a flame standoff here is still corresponding to what's called as an attached flame. We are magnifying the region in the vicinity of the burner rim corner particularly and trying to decipher this standoff, but this is still an attached flame. What we mean by a lifted flame is when now the flame gets significantly lifted away from the burner, because now it can get very reactive as you now have a fuel rich mixture that's coming in and mixing with the ambient. The flame can actually get significantly reactive, right. So it can get stabilized further out, completely away from the rim, not anywhere near the vicinity of the rim. So that is actually a lifted flame, and it has its envelope as well, and this is actually the blowout of the lifted flame. This means this is an edge where the lifted flame also blows out. So that is distinguished between blow off and blow out. Blow off is a terminology that is used for a attached flame, and blow out is for the lifted flame to just go out, okay. And this curve then becomes basically the lift transition from an attached flame to a lifted flame. This curve becomes like a transition that causes the lifting So that means if you now are fixing your fuel concentration and kept on increasing your velocity, you should now lift at this particular point, right? And interestingly, this curve corresponds to what is now called as a drop off or a drop back. What does that mean? If you now have a difference between these two, right, what that basically tells you is, if I now have a burner and I keep on increasing my velocity and I now have the attached flame trying to desperately hold on to the burner by giving way, it's kind of like elastic thing, right? So the flame is trying to actually get pushed a little bit further and further but still attached, and then it lifts, okay, and then it is actually burning there, and you're like, oops, let me just bring back the velocity so that it can attach. Nah, it won't. It would stay lifted until you decrease the velocity significantly lower than the point when you cause this lifting to happen. That's what is called as a hysteresis, right? So what's going to happen now at that velocity is not going to actually cause a drop back right there. You need to come down to a much lower velocity for the drop back to happen, because now the flame has found a new home where it has got stabilized and it's beginning to get comfortable there. It's going to stay there even if the velocity were lower and would allow a attached flame to happen. So the question of whether you're going to have a lifted flame or an attached flame now begins to depend on which way are you approaching in your velocity direction, for example, right? If you're now going in the increasing direction of velocity, you would stay attached until you went there. If you had a lifted flame to start with at a very high velocity and you keep on decreasing, you will stay lifted until you get to the drawback limit. So this is a region corresponding to both lifted and attached flames. So attached or lifted, right? And so if you want to actually shade this somewhat, you see this region is now going to take shadings from both, and is a common point for both. I would like to point out one thing that we have not talked in detail at all, or as a matter of fact not considered. When we did the tip, right, we talked about flame stretch effects, which is to take into account the flame curvature and flow divergence effects. When we talked about the flame base, where the stabilization happens, we haven't really bothered about that at all, okay? So considering flame stretch effects on flame stabilization alters the concept somewhat. So we could do this. We could do this. We know how the SL changes with flame curvature and flow divergence, as we have seen yesterday, and we could take into account a diluting environment and a progressively changing fuel concentration or reactant concentration effect on SL. So you can take into account a spatially varying SL because of spatially varying concentrations of reactants, and all these things can be taken into account in like a computation, right? In a way we want to calculate this and take this into account, and that changes things somewhat. The other thing that I would like to point out is what we have been primarily talking about is flame stabilization over a burner rim, right? But in general we could be talking about flame propagation in a duct. So for example, when you now think about like a flashback, we'll say okay fine, let it flash back and see what happens, right? So how does the flame propagate further down into the duct? So there are some things that I would like to just say about flame propagation through the duct before we get to the next step. Right. Now here what we have to think about is how is the duct. Okay. So far we have been thinking about like a Bunsen burner, where typically we are looking at a Bunsen burner that is vertical, and you now have a flame that is stabilized above the rim of the Bunsen burner, and then the products go out up, right. Now implicitly in our minds we have been adopting a gravitational field that's acting on these things, and therefore there is a effect of buoyancy on these gases, where the lighter gases would actually go up and the denser gases would stay down, and the lighter gases are made lighter because of a higher temperature, mainly for the products, when compared to the colder gases being the reactants, and therefore denser. And so long as you now have a flame that is demarcating denser gases being down here and the lighter gases being above, that is where they belong, so nothing is difficult or different, right. So what we would like to think about is a horizontal duct, for example, and you now may fill this with a reactant mixture, let us suppose methane and methane air, right. Keep it open on both sides for your safety, you don't want to have transition to detonation here, right. So you now ignite from one end and now allow for the flame to propagate, alright. Now of course there are lots of nice interesting studies about flame propagations in tubes that are progressively of smaller dimensions, and then you will find how the flame convolutes and so on, right. And you see that the gases behind have to flow away from the flame for a deflagration, and then they begin to actually have a velocity profile as the flame propagates and all those things, okay. So but that's because of the no slip boundary condition. Oh, that's pretty interesting. So we'll now talk about flame propagation in a duct rather than being stabilized on the rim of a rim outside a duct that is vertical. So far what we have been imagining is like having a burner and then having a flame that is stabilized above it, but implicitly in our minds we have a gravitational field that's acting on this, and you see what's going on. You have a gravitational field that is acting downwards, and you now have a flame, reactants are coming up here and products are going up there, and this gravitational field is now going to actually impose a buoyancy effect in which the lighter gases are going to go upwards and the denser gases are going to stay downwards, and lighter gases are made lighter because of a higher temperature, which is mainly for the products, and denser gases are actually for the cold reactants, and in a flame that we have that is stabilized, the cold reactants are below and the hot products are above, and then you have a fairly stationary flame. But that is not necessarily the case all the time. So the way to actually think about this to begin with is start looking at flame propagation in a duct which is horizontal. So we now consider a duct which is horizontal and fix it up and fill it up with a reactant mixture, let's say methane and air, and you now ignite it at one end and keep the duct ends open so that you don't get into transition to detonation and those kinds of issues. Then you expect a flame propagation to happen, right. And there are lots of nice studies about how this flame propagation happens in this tube, and for progressively smaller tubes how the flame actually curves because the float curves, the flow attains a velocity profile because of the no slip boundary condition, and this is actually the flow that's moving away from the flame and so on. Those are all niceties that we will not really get into. The question that we are asking now is, if I ignite it at this end, you have a flame propagation from left to right. If I ignited it from the other end, would the scenario be different, except that the flame propagation is going to be from right to left? In a gravitational field that is acting only one way, we don't expect a change. On the other hand, if you now consider a vertical duct and you now fill it up with a methane air mixture and you now ignite it at the top, and you now have a flame propagation that is happening downward from the top, you see you have a cold reactant mixture at the bottom and the hot products are going to be at the top, and they are going to flow up, right. Convectively they are flowing up. The buoyancy driving is also going to make them flow up, right, and then you now have a propagation that happens further down and you get a certain flame speed. But what happens when you now have the same vertical duct and you take the same mixture that is in it but ignite it from the bottom? You now begin to have a flame that is actually beginning to propagate upward. The reactants are cold and they are above, and the products are hot, and buoyancy is actually trying to drive them to go up against the deflagration, expecting the deflagration causing an expansion that is making it flow down, right. So if you now look at its momentum balance, the product gas is now going to have a tendency to flow through the flame upwards and contaminate or dilute the reactant gases, and therefore you are now going, sorry, yeah, that's right, therefore the flame speed that you are going to get is different. On top of this, we will also have to factor in the fate of the thermal diffusive instability, that is like perturbation to a planar flame, and how much heat that is going to get conducted versus how much reactant gases are going to get diffused, right, versus now product diffusion as well, and so on the one hand, and also the hydrodynamic instability of what's the fate of a flame that is perturbed from a planar condition with hot gases on one side and cold gases on the other side, where the density jump across this, you now have an instability because of that. All these things eventually lead to the formation of things like cellular flames. That means you don't no longer have a flat flame at all, the flame gets highly wrinkled, okay, and then you get into what's called a cellular instabilities. These are things that are not going to be covered at all, but I wanted to point out a very interesting phenomenon here, where you just have to take a duct and then hold it horizontally and ignite it at either end, or hold it vertically and ignite it at either end, you are going to get significantly different results. Point out something about the flammability limits. This is again like a informative thing rather than an analytical thing. So we had this kind of a curve right at the beginning to look at the dependence of SL on physical and chemical parameters, and what we found was the flame speed actually increases and decreases about a point of phi equal to 1, the equivalence ratio 1, slightly peaking towards fuel rich side, and in fact this is actually something that could be obtained by doing measurements on a Bunsen burner at the shoulder of the flame to look at what its angle is with respect to the incoming flow, or you could actually look at a glass tube apparatus measured set up like this and then ignited at this end and then see what happens, or you could also have a spherically propagating flame. There are many apparatus that are used for measuring flame speed, and each of them has its own uncertainties because of additional effects that are not considered typically in the flame speed experiment. For example, in a spherical flame you have a flame curvature effect that's coming into picture that is altering the flame speed measurement, and so on. Now what we are talking about here in the context of flammability limits is something that we found the other day, that is we have the flame speed decrease on either side from the maximum and then stop. That means this doesn't really go to 0, you don't have any flame at all propagating on either side here, and this is what is called as a fuel lean limit, and this is what is called as a fuel rich limit. And at these limits you have a significant role for chemical kinetics coming in. What is the effect of chemical, what are the set of reactions that are happening, and you are now starving the system of one set of reactants, right, or one reactant to start with and then corresponding set of radicals that are there, okay. So the chemistry can significantly play a role over here, and for this reason the flammability limits are somewhat empirical. I mean the knowledge on flammability limits is quite empirical even to this day. You have to significantly work on the theory to be able to explain this correctly. There are some theories which do a good job, like for example a heat loss theory, where you now basically say that there is a lot of heat loss to the surroundings when you're now looking at these limits and so on. And keep in mind what I meant by heat loss yesterday, which is heat loss to non-participating reactants, right. So you could have that situation, but we are not going to get into all those details. I am just going to factually state that you have these limits, and what does it depend on? See, effectively the controls that we have in any experiment are the temperature and pressure. The pressure is kept constant, and we are talking about reactant temperatures. How do we actually change these with the reactant temperatures? The effect of temperature is a lot more straightforward. You typically have a increase in the envelope of the flammability when you now increase your initial temperature Ti, and the flammability limits expand linearly with initial temperature. And this linear, so that means you can think about like a coefficient, in the sense what is the rate at which the fuel lean limit expands as you increase the temperature, and how does the fuel rich limit expand as you increase the temperature per unit degree, for example, right. So what you will find is the slope. If you now try to actually look at how the slope of the limit change is with temperature, you will find that the coefficient or the slope for this relationship is higher for the fuel rich limit. That means the fuel rich limit changes more steeply with increase in temperature, right. So that is to say, basically, you know, this gap should be quite less when compared to that gap, although this picture doesn't reflect that significantly, okay. And keep in mind, when we say expand, we expect the fuel lean limit to decrease and the fuel rich limit to increase in phi. The corresponding phi should actually decrease for lean and increase for rich, okay. So if you're asked to do some kind of calculations given what is this linear dependence, you should factor in that lean is going to decrease and rich is going to increase. To the pressure dependence. So pressure dependence is more significant than the temperature dependence. Usually you find a dependence that sort of looks like this. If you now have a P versus, let's say, phi, you have a relatively weaker dependence, relatively weaker, for the lean limit, I'm sorry. Still it's sort of linear, okay. So over a range of pressures it's weakly linear, and then almost remains constant over a smaller range if you think about it, and then flattens out beyond at a certain low pressure, beyond which you just have no flammability at all. But then it is more sensitive at the rich limit. So this is the rich limit and this is the lean limit. If you now look at how this works, this is actually controlled by like a second order mechanism at low pressure, and this is controlled by a first order mechanism at high pressure. High pressure or low pressure could be substantially on either side of atmospheric, right. So we are now looking at tens of bars over here. This is subatmospheric pressure over here, okay. And one more thing I would like to point out in these kinds of things is the duct diameter plays a role. Plays a role in determining the flammability limits, typically for small ducts. So if you now look at small ducts, as this diameter actually decreases, then you get into two problems. One, you could actually extinguish rapidly or within the limit of what was actually deduced with a higher diameter, or harder to ignite. As you now go to smaller and smaller diameters, you may not even be able to ignite the mixture, right? And this is typically true at lower and lower pressures. So you now have a fairly good sensitivity of the flammability limits to the duct diameter at lower pressure, essentially because of the difficulty to ignite, or even if you ignite you could have an extinction happen within a narrow range of equivalence ratios, giving a fairly narrow range of flammability limits correspondingly. And I'd like to point out that this leads to something called quenching, which we will discuss next.